In this chapter, we study the dynamic and real-time vehicle routing problem. The goal is to keep improving last-mile routes while the day is already in progress. Unlike static routing, new delivery requests arrive continuously and traffic conditions can shift quickly. That means an hour-old plan can become inefficient or even infeasible, so the dispatch system must adapt in near real time. Picture downtown Seattle at 2:47 p.m. on a busy Tuesday. Maria is dispatching a same-day fleet for quick logistics, and new requests appear on her screen every few minutes. Some jobs are time-critical, like a prescription delivery, while others are deadline-driven, like a gift that must arrive before 6 p.m. Each request arrives with a priority and a time window that affects how it should be routed. This is dynamic routing because the full customer set is not known up front. Requests arrive during execution, and the system may also face cancellations or sudden constraints. The fleet state changes continuously. Vehicles move, remaining capacity changes after each drop, and the best route sequence can change when travel times shift. The routing task is therefore an ongoing control problem. Real-time routing is hard because service quality and feasibility can conflict. Tight time windows force immediate action, but constant rerouting can create disruption for drivers and customers. So, a practical system must balance responsiveness with stability. It needs to accept, postpone, or reject requests based on feasibility, while also avoiding excessive route churn. This deck uses 5 tiers. Tier 1 is the mathematical formulation: state, request arrivals, objective, and constraints. Tier 4 uses neuroevolutionary learning for fast decision-making. Tier 6 uses distributed multi-agent coordination. Tier 7 integrates human judgment with artificial intelligence. Tier 9 explores quantum computing as a route to real-time optimization at large scale. Tier 1 frames the system as a dynamic decision process. Instead of optimizing once, we define a state that captures what matters right now, and we update decisions as time advances. The key shift is from building a single best route plan to building an adaptive policy that can absorb new requests and changing travel times while maintaining service feasibility. This slide defines the state. It includes current vehicle positions, the planned routes in progress, and the set of active requests that still need service. It also includes capacity constraints and environmental parameters like traffic. Operationally, this is the information a dispatcher needs to evaluate the next assignment or insertion decision. Request arrivals are modeled with a time-varying arrival rate. In real operations, the arrival intensity changes over the day, with peaks during certain hours. A non-homogeneous Poisson model captures this by describing the probability of observing a certain number of new requests in the next short interval, given the current time-dependent arrival rate. Each request is represented by its origin, destination, quantity, and the time it arrives. It also includes a time window and a priority. Priority matters because the system may reroute immediately for high-priority jobs, while postponing or even rejecting lower-priority jobs when the fleet is constrained. The objective in a dynamic environment balances multiple goals. We want low travel cost, but we also care about customer waiting time and penalties for rejected requests. Importantly, we also account for route modification cost, because frequent route changes have operational friction and can reduce reliability. These constraints formalize feasibility at each time. Requests must be served, vehicle capacity must not be exceeded, and service start times must remain within time windows. There is also a sequencing feasibility rule. Once you decide an order of stops, each subsequent stop must be reachable in time given the time-dependent travel times. This visualization shows how the system evolves. New requests arrive, vehicles move, and routes are adapted through insertions and reassignments. The main point is that routing is a continuous process. The system is repeatedly adjusting a living plan while vehicles are already executing it. In the 3-vehicle example, each vehicle has an initial plan at 9 a.m. At 9:15 a.m., 2 new requests arrive with tight windows. The model evaluates feasible insertions and reassignments. The example assigns request A to vehicle 3 with detour cost 2.3 units, and request B to vehicle 1 with cost increase 1.7 units, serving both within their time windows. Tier 4 introduces neuroevolutionary learning. The idea is to learn routing intelligence that can react quickly instead of solving a heavy optimization problem from scratch after each change. Neuroevolution involves both network topology and weights, producing decision policies that can generalize across different dynamic scenarios. This figure illustrates the neuroevolutionary architecture. The agent receives a compact encoding of the current system state. It outputs decisions that guide assignment and route modification. Over generations, the system selects network designs that reduce cost while respecting time windows and priorities. In this part, the code makes the slide method executable. The key classes visible here include the network genome and DVRP neuroagent classes. Key functions in this chunk include encode state. You will notice logic related to fitness, mutation. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include forward pass. You will notice logic related to route. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, we move from the idea to the mechanics of the implementation. The key class visible here is the DVRP Neuroevolution class. Key functions in this chunk include initialize population. You will notice logic related to mutation, population. As you read it, focus on the sequence of steps and which variables are carried forward, because that is where most implementation bugs hide. Also check stopping rules and guardrails, so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities, so you can verify that the update logic behaves as expected. In this part, you can see the implementation details in action. Key functions in this chunk include evaluate fitness and tournament selection. You will notice logic related to fitness, population. As you read it, follow the data flow from inputs to outputs and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, the code makes the slide method executable. Key functions in this chunk include crossover genomes, mutate genome, and evolve routing intelligence. You will notice logic related to mutation, crossover. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, we move from the idea to the mechanics of the implementation. You will notice logic related to fitness, mutation, crossover, population. As you read it, focus on the sequence of steps and which variables are carried forward because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, you can see the implementation details in action. You will notice logic related to fitness, population. As you read it, track what is computed, what is stored, and what gets updated each iteration. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. This slide summarizes the concrete training results. The neuroevolutionary system is trained on 20 DVRP scenarios over a 4-hour simulation, evolving over 50 generations with population 40. Compared to a nearest neighbor heuristic, average cost improves from 847.3 to 623.1, and response time improves from 12 milliseconds to 8 milliseconds. Tier 6 shifts from centralized optimization to distributed intelligence. Vehicles, zones, requests, and infrastructure can act as autonomous agents. The key benefit is scalability and resilience. Local agents can respond immediately to local changes, while negotiation protocols help maintain good system-wide outcomes. This figure shows the multi-agent architecture. Vehicle agents handle local routing, zone agents coordinate regional resources, request agents represent service needs, and infrastructure agents provide environmental updates. Together, these agents create emergent coordination without relying on a single centralized solver that could become a bottleneck. This slide defines the bid function used in a contract net-style protocol. When a new request arrives, candidate vehicles compute bids reflecting detour cost, delay risk, capacity utilization, and future impact. Operationally, this allows fast, decentralized assignment decisions that still consider multiple criteria, not just distance. In the lunch hour coordination example, the system has 15 vehicles across 4 zones, with many active and newly arriving requests. An urgent pharmaceutical delivery triggers bidding among nearby vehicles. The selected vehicle takes the urgent job, and lower priority work is rebalanced through secondary negotiations. Reported overhead is 47 milliseconds with measurable improvement in average delivery time and utilization. Tier 7 is the human and artificial intelligence symbiosis model. The AI processes real-time data and proposes route changes, while humans provide context, exception handling, and relationship-aware prioritization. The goal is not to replace the dispatcher, but to increase decision quality and speed while maintaining accountability and customer-centric judgment. This figure represents the human and AI interface. A practical interface summarizes recommendations, highlights the reasons, and shows uncertainty and alternatives. That transparency helps dispatchers validate decisions quickly during disruptions, and it improves trust calibration over time. The crisis management example shows the value of collaboration. A major traffic incident affects many routes while urgent deliveries are due soon. The AI explores route combinations quickly and predicts clearance time, while the dispatcher adjusts priorities and negotiates exceptions based on customer criticality. The combined approach achieves superior on-time performance with fewer complaints than either AI-only or human-only operation. Tier 9 explores quantum computing as a way to handle explosive combinatorial complexity in large dynamic routing systems. The idea is to encode routing as a quadratic, unconstrained binary optimization problem and use quantum annealing to search for high-quality solutions fast enough for real-time dispatch. This figure illustrates the quantum computing architecture conceptually. It highlights how quantum hardware could be integrated into a real-time dispatch stack. The practical motivation is speed. When disruptions occur and many requests must be reassigned, the system needs solutions in seconds rather than minutes. This slide shows the quadratic, unconstrained binary optimization, Hamiltonian used for quantum annealing. It combines a travel cost term with penalty terms. One penalty encourages serving each request exactly once, and another enforces capacity feasibility. Choosing penalty weights is crucial so the solver avoids infeasible assignments while still exploring high-quality routes. Quantum state evolution represents a superposition over valid routing configurations. As new requests arrive, the set of valid configurations changes. The promise is that the system can adapt rapidly by updating constraints and continuing the search, rather than restarting a full optimization cycle every time conditions change. The real-time scale example illustrates why advanced computation matters. At large scale, classical optimization can be too slow for rapid re-optimization. The reported results show a dramatic reduction in optimization time, lower request rejection, and higher utilization. Even if these numbers are scenario-dependent, the direction is clear. Speed and quality improve as computation becomes more powerful. These practice questions help you apply each tier. Start by writing a dynamic formulation with arrivals, time windows, and feasibility constraints. Then design a neuroevolutionary training setup, a multi-agent negotiation protocol, an explainable human-in-the-loop interface, and finally a small quadratic, unconstrained binary optimization encoding for quantum optimization. To close, remember that dynamic routing is continuous adaptation under uncertainty. Tier 1 provides structure and clarity through a state-based model. Learning and distributed coordination improve responsiveness at scale. Human and artificial intelligence collaboration adds judgment and accountability. And quantum approaches explore what might be feasible for very large systems in real time.